Good morning still, everyone. As Andrew's mentioned, I'm David Cafferty. I'll be joined by Raffelle, and we've left Sarah down there in order for that it's not a bit of a song and dance act, but we'll be calling her up towards the end. Just to sort of introduce, so what we're going to be talking about really is specifically the field of higher density complex urban settings. So we've heard a lot about SAP this morning, and what you're going to be hearing from us will obviously touch on SAP, and there's some comparative analysis. And obviously, what we're talking about is our use of dynamic simulation in our design process to deliver added value to our design process. What we do, as Andrew's mentioned, I take overall control of our development sector portfolio. So most of the work we do is for developers and developments that make money. They tend to be higher density developments, etc. And I want to talk a bit really about our design process and how we think we deliver added value for our clients in a very kind of meaningful way. We always want our design process to become better and better. We therefore look for innovation to do that. We've had a long-term relationship with the University of Strathclyde. I'm a graduate of the University of Strathclyde, and obviously through that process we've become very involved with IES and therefore the dynamic simulation process. So therefore, just looking at the scheme, this is the scheme we're actually talking about. I haven't titled it simply because it's in the planning process at the moment, and our clients really don't like too much drama about projects when they're in the planning process because there's still a lot of risk involved. But what we are going to do, we're going to talk about the improving standards that we have to meet, and what we find when we are designing our projects, and hopefully getting a bit of feedback on that. As you know, the kind of current standard for building regs is basically the baseline is 2013. And what we're really asking ourselves, the question is, can we achieve these standards with good design methodology, great quality passive design, but essentially without relying on renewables, because that's what we try and achieve. And what we do find is that if we are actually using, and again, this goes back to the circumstance that in the residential process at the moment, in residential sector, in the commercial sector, you can use dynamic simulation already. In the residential sector, you're only really allowed to use SAP. We tend to think that that's not, we need to move on from that because the building typology in residential is becoming more sophisticated. SAP is a slightly more historical tool that is probably more compatible, in our view, with more volume house types. When we look at high density, highly complex residential schemes, we think we need another kind of avenue of analysis, as it were. So Part L requires a 25% reduction in carbon emissions, but the London plan, which is basically the only relevant benchmark as far as I'm concerned, requires me to get to 35% improvement on it. So the 25% is essentially irrelevant. And what that obviously means is if you fail to achieve the 35%, you start paying either carbon offset payments, or of course you can usually achieve it by bolting on renewables. So what we do inherently believe in, though, is the be lean, be clean, be green cycle. But what we want to do is we don't want to rely on the be green, but we want to make the benchmarks through good quality design. Using SAP methodology, this is where we get to essentially. That's where we did get to on the scheme. So without any renewables on the scheme, we found we could achieve, using a SAP tool, just over the 25% improvement for building regs, but we couldn't get to the 35%. Therefore, our client was going to have to pay carbon offset payments or add on renewables to an already very, very expensive scheme. Maybe that's our fault. What an integrated design approach does, and again, at this point I should say that we are a full BIM practice, so every single project we ever do is done in full 3D. The level of BIM that we apply is obviously dependent on our clients' requirements, but essentially everything we do starts off with a BIM process in full 3D, and therefore that gives us the opportunity to use the models we create to link into tools such as the IES and DSM tools to analyse our building performance in a much more, I think, in a much more accurate and a much more sophisticated way. Obviously, dynamically simulating, you're using climatic data, you're considering temperature differentials between inside and out, and you're doing it in a very dynamic fashion. But what you're also doing is you're also seeing the real benefits of the passive design techniques. So when we incorporate, we obviously are considering orientation. It's a fundamental aspect of DSM, relative to the question earlier from the Stuart Milne group, for example. But what we can do, and obviously through specification, our apartments are generally whole house ventilation systems anyway, so we can create more tightly controlled air tightness environments, for example, and we can consider the benefits of a much more holistic process of design. And therefore, what essentially we were able to demonstrate that by using a DSM-supported approach, without changing the design at all, we actually were demonstrating that we could reach the 35% improvement using a DSM process. Interestingly, we have actually submitted an exercise to the borough in question. So with planning, obviously the 35% improvement is our London plan requirement. The response we've had at the moment, because we're obviously trying to save our client money, we're trying to save them any carbon offset payments. The response we've had at the moment is, if the GLA are happy with this approach, then we'll be happy with the approach. I think at the moment we've kind of got to an impasse there, though, because we don't really know who at the GLA to ask if the approach is okay. Nobody seems to know. However, we hope we'll win our argument for our client anyway. So I think, again, there's just, again, a summary of going from 2013 through the same building analysis, essentially. And interestingly, putting that in the context of the historic improvements that we've made over the years in building. Andrew, when you and I first met, way back in the very early box, you can see the level. And this is actually a space heating demand analysis, but it does show how the standards over not too many years have dropped significantly. And it's all down to you. And I think the point we're beginning to make there is that, actually, the future avenues for saving energy and space heating is becoming very, very minimal, because we're actually dealing with such a small quantum. And so effectively that actually shows the improvement on the space heating demand component of that overall energy performance. So the differential in performance is very, very significant, albeit that's focused on space heating. So I've tried to avoid any sort of technical stuff. I'm going to hand over to my more learned colleague Raffelle, who will give you a little bit more of the technical stuff. So if it comes to questions at the end, ask him the technical stuff, okay? Thank you.
Thank you. Yes, I will show you an example of this integration process, which provides this big difference. It's a very simple example. This is our essential simulation framework we use. It is going from the 3D modeling, the natural ventilation, CFD airflows, natural light design and artificial light, all the mechanical system, and the design of the energy provision. All is fit into a life cycle costing analysis that is provided to actually support decision-making process. Everything is driven around indoor environmental quality aspect, which is actually corresponding to going into increase the quality and while reducing the impact and the energy demand. And while we go into some detail of these aspects, we need to consider that the main thing is still the architectural design. This is what actually provides the good performance. We are not addressing all the passive technologies and strategies we implemented. We are just focusing on a few elements. These are the natural ventilation connected to the mechanical ventilation and some winter gardens, which are extensively provided in the development. Natural ventilation will be used whenever the outdoor temperature is suitable for that. That means whenever it is higher than, say, 16 degrees, more or less. Otherwise, the mechanical ventilation will kick in. And this part of the envelope is providing a dynamic envelope indeed, and the winter gardens will give the ability of opening or closing the envelope to provide additional insulation, further protection with a buffer zone, noise protection, increase solar gains, or even better control of solar gains. And on top of that, we'll be providing an amenity space which is available all year round. While the mechanical system is simply bypassing the natural ventilation, providing fresh air, and also including some heat recovery, which is extracting heat from the used air. That's a simple mechanism. How we simulate natural ventilation is using real hourly data from the climate database and connecting that with the simulation of operating the windows either by the user or by an automated system. And we have some different types of windows here, depending on the location. While the mechanical system is designed through a network, a simple network going through the different ambience, including the winter gardens. In this case, we apply this network to every apartment where we wanted to know exactly the difference depending on the aspect and exposure of the apartment. And this is simply the way these two systems, when in mechanical mode, work together. From the left, we see the fresh air, which is let into the winter garden, preheated there, and then let into the heat recovery unit, where it is preheated again through the heat recovery, taking heat from the exhaust air, and then finally delivered to the apartment. That process, that sequence is summarized here for a sample day in February, a rather cold day. So in the bottom we see the outdoor temperature, and then the temperature has rise within the winter garden, then rise again within the heat recovery system, and on top there we see the final space as conditioned. And you see the difference there is quite tiny. This is the same process, same sequence in different location, showing the importance of addressing a dynamic approach. On the left-hand side, we see a milder effect of that solar gain on that winter garden, which is not exposed as the other on the right-hand side. These are two same apartments at two different levels. There is a stronger solar radiation, so there is a peak there in the temperature within the winter garden. And on top, there is an intervention by either a user or the system to open the windows there, so there is not such a peak. And similarly, this is a distribution of performance over a floor plan at an earlier design stage. And at the time, that was already a good performance range. But a few apartments, as you can see, were not performing as the others. And then design proceeded, and after a few months, we had optimized things, and we got to a much better distribution of performance. Every apartment is performing below 10 kilowatt per square meter per year. Sorry. Finally, this is the overall performance of this portion of the development. Every column is a type, a level of the building, and the last column on the right-hand side is the average performance. That 6.86 is quite a good result for the space conditioning. And if we compare that to some benchmark values, as the zero carbon homes, which would suggest no more than 39, or the passive house with no more than 15, or a survey of recent solar housing development around Europe, which is providing a 10 figure, we are well below that, with 6.8. But what is most important is that we are there increasing the air quality indoor, so we are controlling that to a better air provision, fresh, and we are using standard, good but standard values in air tightness and develop specifications, which we can confirm that through a comprehensive dynamic approach we can correlate different aspects all together and get a better picture of what's really happening in the building at different locations at different times, and that allows for a better economical allocation of resources around, putting insulation where actually needed, or other aspects, just like, say, solar control. And it is also very useful at value engineering, changing the scenario at value engineering, where actually you can further increase performance and further reduce costs, applying the same process. And the bottom line is that when there is a good design, the overall performance of the whole system can be much higher than the cumulative performance of the single parts. And this is why dynamic simulation can be very useful there. And
okay. So just before we call up Sarah, just wanted to close with this slide. So I think what we're sort of saying here is that this is all very measurable. We have had the comment, for example, that the SAP process is the one that should be applied to the residential sector because it's the standard method of measurement. But at the end of the day, our view is this is an empirical process. Therefore, because it's measurable, there's no reason there shouldn't be an optional kind of route to get from A to B, essentially. And I think also what it does is, as we say, it shows you this evolution through time, where the quantum of energy required for space heating now is becoming so minimal. But it's all now, for us, it's very measurable, and we're always looking for ways to measure the improvements we can bring to our design process. And in actual fact, in a funny sort of way, the carbon offset payment thing actually does give us a very measurable demonstration to our clients of how we can save them money. The theoretical carbon offset payment in the scheme that we're talking about is £150,000. So if we can save our client £150,000, then we're very happy to do so. It's built into our design process. And if I can just invite Sarah.
Hi. Okay, so thanks very much, David and Raffelle, for a great presentation in what is a fantastic case study. I'd like to pick up this point, particularly here, further optimisation through smart strategies at the community level. So I was just going to bring a slightly different perspective to this, thinking about the bigger picture, so larger scale developments, sort of mixed use community level smart cities, and also looking up at the horizon a little bit in terms of software development and smart buildings, smart technologies, that type of thing. So first of all, I just wanted to give an overview of what we do for those who don't already know. We are a UK company developing world-leading building performance analysis software. And our sort of statement is that through the use of our technology, any building anywhere in the world can be designed and operated optimally. So we're most known for the new design and retrofit, which is what has been covered in the case study there. But in recent times, we have focused very much on using the core technology to develop the smart communities, looking at building operation as well, so smart building controls, that sort of thing, and then developing decision-making tools for the master planning stage as well. So what I mean by that is taking the data when the building or development is actually operational and looking at that in real time, comparing that with the design scenario, looking at closing the performance gap, some of the things that we've already heard discussed earlier. And we do that through a single model of a building or a community development, a master plan, and a very integrated approach. So a lot of the elements that came through in the case study and which have been highlighted before to do with like ensuring good indoor air quality, a good comfortable environment, reducing overheating, and closing the performance gap can be addressed through the software. But the focus now, I think, for us and for the industry is in the operational phase of buildings, because we can say day one, hand over, this building performs to this level. It's it's got a Part L rating of whatever it might be, an EPC rating of B or C. But actually 6 months into the operation of the building or after 5 years, what does that look like? And that's very much where our technology and R&D is focused at the moment. And scaling that up, as I say, from individual buildings to multiple buildings. So bringing a lot of data together, analysing that potentially in real time to make decisions about where the resources should be placed, within the building in terms of heating, ventilation, whatever it might be, and in the wider site as well. So I know you can't read the text on there, but this is actually the government's sort of level 2 BIM strategy for a project simplified. And the point here is that I would like to make is that we're already bringing operational data from that phase of the building back into the design of subsequent buildings, and comparing the design and the operational scenario. So we can close the loop on the soft landings metrics, which are mandated as part of the government's BIM strategy, on things like energy, carbon, cost, comfort, whatever those metrics might be, you know, employer requirements such as BREEAM Excellent, all of that can be captured, analysed and exchanged through design, construction and operation. So level 3 BIM then, the government set out their strategy for the next phase, which is over potentially the next decade. The strategy was published in February this year. And we're looking at here integrating the Internet of Things, and this is where it starts to get a bit sort of futuristic, so bear with me. Advanced data analytics and the digital economy to enable us to firstly plan and design infrastructure more effectively, and then to build that infrastructure at a lower cost. And for the citizens, the users, the occupants, the people that are moving around, to make best use of that built environment that we already have. So although we may be quite a way out from realising what Digital Built Britain sets out to achieve, we do see examples in everyday life of very smart technology used in a domestic setting. So the Nest thermostats would be one example that I would hold up and say this is where we're going really, if you bring it back down to the individual building scale. So these are clever little thermostats, cloud-based control, learning algorithms built in there, so you can from your smartphone tell the heating system when you'll be home and what temperature the house should be at when you get in. Or it can learn based on usage patterns. Say you come home early one Thursday and it decides that it's going to start putting the heating on a bit earlier every Thursday thereafter, or you can reset it. But what really becomes, where we really see the benefit of this smart technology is in the fact that all of these things speak to one another. And that's really what we're talking about in the context of smart buildings and smart cities, is this interlinking connection of buildings, transport, people, all these different elements of what makes up the built environment, and how we can make it better. So in this case, if the smoke alarm senses carbon monoxide, it will automatically shut off the boiler through the thermostat. The smoke alarms also get motion detectors, so it can sense when somebody comes in and it can, you know, adjust things to suit. So it is smart stuff. We see examples of this in a commercial building setting as well. I think the Schneider HQ in Paris is quite a good example of an intelligent building. A couple of examples of how they've approached it is every visitor and employee in the building has a little chipped visitor pass. So the building systems know how many people are in that building and how they're moving around and where they are at any one time. And you can start to sort of control systems on that basis as well. In that building also, if you book a meeting room, it will bring on the lights and AC at the scheduled meeting start time. And if the room is unoccupied after 10 minutes, everything shuts off again. So we can start, I mean, it's not really rocket science. When we start talking about smart buildings and smart cities, it breaks down into little elements of smart technology. So I just wanted to really finish off by saying that we see buildings as the connectors between the citizens, the transport, energy, water, waste, and therefore core to any smart city approach. We use operational data, and it'll be very interesting to see from the HLM example how that pans out. So actually capturing the data once the building's up and running and occupied, and feeding that back in. Were the assumptions that we made correct? What learnings can we take to input to future projects? We use half-hourly, we as a consultancy firm as well use half-hourly data to inform things like district energy schemes. So we've worked with Glasgow City Council, carried out a full proof of concept study, looking at how different buildings can interact with one another in terms of community level energy generation and sharing. Now these concepts are not new. We have used district heating within a social housing context for decades. We've used energy centres in larger campuses, hospitals, etc. But what we're talking about with the smart cities principle is extending that to then include things like transport and people movement and piloting technologies that will link everything together. So integrated systems and real-time data will help planners and designers to create smart cities, smart communities and smart buildings. And we have the technology, and all of us together have the skills to help and be part of that digital future. That was all I wanted to say. Okay, thank you.
Right, just before we break for lunch, I thought it was appropriate to ask Sarah, Raffelle and David to come to the front.
Do we have any
messages, please? And if you could say your name, company and who your question's addressed to.
Hello, Bill Dunster, Zedd Factory. Just a quick question for the architects at HLM. What's the construction cost per square metre for the triangular urban block that you showed in your sample?
Well, that's quite a complex question to answer. The reason for that is the whole development is built in a number of phases with interconnected basements, etc. So that there's a lot of cost elements that might be deemed as abnormal. It's also in the heart of Chelsea. It's also it's partly very high quality private residential and partly social housing. So there's a whole mixed bag of costs attached to it. But it's at a cost level that you would associate with that type of development in that area. But I actually don't want to go any further.
Go on, give me a clue. Come on, I mean, it's very important because we're talking about how to justify making these ideas cost effective, and you know you're whittling away at the energy and trying to deliver the the best possible result. Talking about saving 150 grand here and there, but I just want to have a clue on what your construction cost per square metre might be, because that puts it all in perspective.
It's going to be in the region of 350 to 400 pounds a square foot, but that's because there's a lot of, well, it's all tenure blind and it's a very, very high
Cost per square metre?
Well, times that by 10. Well, 10.7614 or 764.
So £3,000 to £4,000 a square metre.
Yeah.
So the cost of the energy saving specification is absolutely minute compared to the construction cost of the project.
Well, that point can be argued, but I think it's still important to not use the energy as well. And I think that the point we're really making is about the dynamic simulation process, is giving us better feedback. It's not just in the savings. What it's doing is it's giving us the opportunity to better understand the way energy is performing, the way the building is performing, and so make the right decisions. That we actually find that sometimes, and again, going back to a SAP analysis, we feel that SAP can sometimes almost encourage us to make the wrong design decisions because of it's a simplified process. We're actually looking at the whole thing much more dynamically. We're actually getting a much better focus on the best decision-making process for passive design. But I do understand in cost terms, we may be talking about a small quantum, but at the end of the day, that particular context demands an incredibly high specification level, and that we are required to provide by the local authority and so on and so forth. But energy is still important.
No, my question was actually, why isn't it a higher specification, not a lower?
Well, the I think the answer to the question why is it's not a higher specification, I think, is explained in the presentation, because what it's demonstrated is that the specification we've achieved at what we would call just very good levels, whereby the actual space heating energy consumption is almost minimal. So there's little point in adding more cost to make further savings, because there's nothing left to save.
Sarah Lewis, Barron Smith Architects. Another question for the architecture team. What sort of because it's great to see all the upfront evaluation and all of the dynamic simulation, but what sort of post-occupancy evaluation and monitoring strategy do you have in place to see whether the calculations that you're making at design stage are actually being seen at occupancy?
Well, I think in terms of post-occupancy evaluation, we have got the systems in place. I think we'd have to be honest and say we haven't done a lot of that yet, but I think that's where we see the future going. And in order to actually get that type of feedback, what we actually have done in terms of this work, because we want to have the debate with the GLA regarding the methodology, is we actually have and are commissioning the BRE to validate the process so that they can validate the performance in terms of calculation. What you can't always do, of course, is control behaviour. So behaviour of buildings will within buildings will have an impact on post-occupancy evaluation results.
Absolutely. I mean, I think one of the things about doing the post-occupancy evaluation is it helps to feed back into your simulations in the future, because you get a better idea of how the occupants do behave. But it's great to hear that you're doing some work on that.
I can just add to that there is a scenario where we actually should be looking at an improvement in performance thanks to the users, thanks to the smart technology. We are looking to controls that should be as simple as possible and using automation to make life easy for users. So we're not looking to complex mechanisms. That should happen, and there's nothing against that, and I think we will work on that, perhaps.
Charlotte Booth, an associate at Hodkinson Consultancy. I just had more of a technical question for Raffelle on the dynamic simulation for optimization slide that you had. I just wondered how you went about running the optimization and what you applied to get those, because all of your units kind of went from being a range of fabric energy efficiencies, didn't they, to the same?
Well, that was mostly thanks to the design, architectural design, the positioning of the windows, a new planning of the apartments. At the time, they weren't not so good in performing towards solar gains and solar access. And that was making the difference indeed. Not much more. I think we also used some more higher improvement by the winter gardens.
So it was before planning, and so you're able to move the windows around?
Yeah, that is all in the history of design, yes.
This is a very integrated component of the design in the pre-planning stages.
Okay. I think that's all the questions. Can we give our trio a